Okay, hey students, for today we will be discussing about pages 15, 16, 17, 18, and 19. So I want you to kindly get those pages, so pause for a while and prepare those pages. Now sharing to you the targets for this discussion. First target, differentiate between the concept of work in physics and in everyday language. Second target, determine work done by a constant force. Third, illustrate the connection between work and energy. And lastly, calculate kinetic and gravitational potential energy. So this discussion class focuses all about work and energy. Now here is a question. When do we say that a person does work? Now in everyday language, the term work refers to any activity that requires muscular or mental effort. But in science, it's actually different, specifically in physics, because we can only say that there is work done when a force produces motion. Now there is actually, we actually have a condition in order to say that there is work done on an object. First condition, force is acting on the object. So there should be a force applied to a certain object. And not just that, object must move. So there should be a displacement. And lastly, movement is in the same direction, or movement is in the direction of the force. So meaning to say, the movement of the object must be in the same direction as the direction of the force. So again, the three conditions in order for us to say that there is work done. First one, there should be a force applied or acting on an object. Second condition, object must move. And third condition, the movement of the object should be in the same direction as the force applied to it. The example for that is when you pull a box along the floor. Now the box here moves as the same direction as the force. Your force is going upward and the direction of the box is also going upward. Therefore, we can say that in this example, there is a work done on the box. Again, let us examine the conditions. First condition, there must be a force applied. Of course, there is a force applied. Check. Second condition, the object must move. Check. And third condition, the direction of the object must be in the same direction as the force. And as you can see, force and displacement is in the same direction. So, check. Now, scientifically class, work is defined as the product of displacement and the component of the force parallel to the displacement. In symbol, we have the formula W is equal to FD, wherein W means work, F means the force applied, and D means the displacement. Recall that the unit for force is Newton, and the unit for displacement is meter. Meaning to say, the unit for work is Newton times meter. And Newton times meter is actually equal to joules. In symbol, we have capital letter J. Now here's a sample problem. How much work is done when a constant force of 15 Newton is used to push a rectangular cart through a displacement of 15 meters? Now, always remember in solving problems, we follow three steps. G, F, S. Okay, G means the given. By the way, in illustration, this is how it looks like. We have a rectangular cart and it moves 15 meters after applied by 15 newtons of force. So let's proceed to solving the problem. Given, let's identify the given. First one, we are given with a force of 50 newtons. Remember, in putting the given, please indicate the physical quantity as well as the magnitude with units. Second given, we have the displacement of 15 meters. After that is the find. What is asked in the problem? It's the how much work is done. So we have W. Solution. Always remember that in your solution, you always start writing the formula. And our formula is W is equal to F times D. Next step, let us substitute our given. We have a force of 15 Newton multiplied by the displacement of 15 meters. So let us combine 50 times 15, that's 750. And Newton times meter, of course, Newton meter. And remember that Newton meter is equivalent to joules. So the final answer is 750 joules. There is a 750 joules of work done when a constant force of 50 Newton is used to push a rectangular cart through a displacement of 15 meters. Okay, we have the second problem. How much work must be done to raise a 10-kilogram box 2 meters above the ground? So we have the illustration, a box lifted 2 meters above the ground, having a mass of 10 kilograms. Again and again, in solving problems, always start by identifying the given. And our given in this problem, we have the mass of 10 kilograms, we have the distance or displacement of 2 meters. Now, what is asked in the problem? We are looking for the work. And in solution, always start by writing the formula. Now, our formula here, remember that the formula for work is W is equal to FD. But notice in the problem that you are not given the force. Meaning to say, we need to get first or solve the force here. Now, how are we going to solve for the force? Remember that force is equal to mass times acceleration. So we have here, our formula now is mgh. Meaning, m is the mass, g is the acceleration due to gravity, and our displacement or height is just the same. Now let's substitute the values. We have the mass of 10 kilograms times the acceleration due to gravity, which is equal to 9.8 meters per second squared, times the height or the displacement of 2 meters. Now let us combine them. It's equivalent to 196 kilograms meter squared per second squared. And remember that kilogram meter squared per second squared, it's just equal to joules. So the final answer is 196 joules of work. Now let us answer the exercise in your page 15. You have there a series of situations, and you are asked to determine if there is work done on the situation and give a reason why. First situation. Suppose you pushed against an immovable concrete wall for 5 minutes. Did you do work on the wall? So the answer here is, of course, no, because you are pushing an immovable concrete wall. Though you apply force on it, you achieve the first condition, but the second condition is not met. The object being applied by a certain force did not move. So meaning to say, in this situation, there is no work done on the concrete wall. We have second scenario or situation. Suppose you tug a stubborn carabao which refuses to budge. You get tired doing so. Are you doing work? Still here, the answer is no. You did not do work on the carabao because the carabao, remember, it refuses to budge. It refuses to move. So, the object being applied by a force did not move. The second condition was not met. Next situation. A jumbo jet taxis on a straight level runway. Thus, the force of gravity do work on the plane. So, remember that we are focusing here of the force of gravity. And what is the direction of the force of gravity? It is always towards the center of the earth or downward direction, right? But the movement of the jumbo jet is along a straight level runway. It's along a horizontal plane, and the gravity is vertical. Meaning to say, the direction of the motion of the jet is not the same as the direction of the force of gravity. So the answer is still no, there is no work done on the jet by the force of gravity. Now here, I just want to emphasize that if the force is perpendicular to the displacement, there is a zero work. There is no work done. For example, this man here carrying some baggage. Now, the direction of the force applied by the man is going upward. But the man is walking towards a horizontal path. So the force is upward, but the displacement is going or along a horizontal direction. So that's what we say. That's what we call as perpendicular. And if this is the case, it's always zero work. There is no work done on the object. Now, does the centripetal force do work on an object in uniform circular motion? Okay, so centripetal force. And remember that centripetal force is a center-seeking force. So the direction of the centripetal force is towards the center of a circle. And if the object is moving in uniform circular motion, so it is not the same as the direction of the centripetal force. So third condition was not met. Meaning to say, still, no work is done in this situation. Now let's move on to gravitational potential and kinetic energy. Now, what is gravitational potential energy? It is the stored energy possessed by objects lifted at a certain height. So any object lifted at a certain height, it possesses gravitational potential energy. Now we can get the gravitational potential energy of a certain object using this formula. U is equal to mgh, wherein U is the gravitational potential energy, m is of course the mass of the object, g is the acceleration due to gravity, and h, that is the height. Okay? Now how about kinetic energy? Kinetic energy is the energy possessed by moving objects. Any object that is moving, it has kinetic energy. Now we can calculate the value of the kinetic energy of a moving object using this formula. K is equal to 1/2 mv squared, wherein K means the kinetic energy, 1/2 it's just constant, we have m as the mass, and v as the velocity or the speed of the object. Okay, here's a question. How is work related to energy? Whenever you do work on an object, the work done represents the amount of energy transformed from one form to another. For example, if you throw a stone, you do work on the stone. You transform the chemical energy of your body obtained from the food you eat into the kinetic energy of the stone. In fact, class, energy is the capacity. It is defined as the capacity to do work. Okay, meaning to say energy is just equivalent to the work done on a certain object. Let's take this as an example. A weight being pulled upward by a pulley. Since it is being pulled upward, it gains a height, it possesses potential energy. That amount of potential energy is just equal to the amount of work done in lifting that weight. Now, if we are going to cut the string, okay, what will happen to the weight? Of course, it will fall downward. It moves. It is moving, so it gains kinetic energy. From potential energy transformed to kinetic energy. And as it hits a certain object, it does work on the object. Okay, now let us answer the exercises in your page 18. Okay, for number 1, a book has a mass of 1.5 kilograms. If it is raised a distance of 0.5 meters from the table, what is its acquired gravitational potential energy relative to the table? So of course, in solving problems, we identify the given. Then our given here, we have the mass of 1.5 kilograms. We have the distance or the height of 0.5 meters. And okay, we are looking for the potential energy, U. In the solution, start by writing the formula. And the formula for Gravitational potential energy is U is equal to mgh. Substitute the given. We have a mass of 1.5 kilograms times the acceleration due to gravity, which is 9.8 meters per second squared, times the height of 0.5 meters. Okay, let's combine. If you are going to multiply it, you will get 7.35 kilogram meters squared per second squared, and it's equivalent to 7.35 joules. Suppose instead of being on Earth, the table and book in item number 1 are on the moon. What happens to the acquired gravitational energy of the book? So let's go back to number 1. Our answer here is 7.35 joules on Earth. Now, the answer for number 3, the acquired gravitational energy would be lesser on the moon, because remember, the acceleration due to gravity on Earth is greater than the acceleration due to gravity on the moon. Now, the acceleration due to gravity, the gravitational potential energy on Earth is equal to 7.35 joules, as what we solved in problem number 1. Now, in getting the gravitational potential energy on Earth, on moon, what are we going to do is just we divide the gravitational potential energy on Earth by 6. So we have 7.35 joules divided by 6, and it's equal to 1.23 joules. Now for your exercises in page 19, you have problem number 1. What is the kinetic energy of a 3 kilogram object moving at 7 meters per second? So let's identify the given. We have the mass of 3 kilograms. We have the speed of 7 meters per second. And we are looking for the kinetic energy. Okay, in your solution, always start by writing the formula. And the formula for kinetic energy is K is equal to 1/2 mv squared. Let's substitute the given. 1/2 times mass of 3 kilograms times the speed of 7 meters per second raised to the power of 2. So first, let us get the second power of 7 meters per second. So we have 49 meters squared seconds squared. And let's combine everything. We will get 73.5 joules. For problem number 2, what is the kinetic energy of an object at rest? And the answer here, the kinetic energy of an object at rest is always equal to 0, because only moving objects possesses kinetic energy. So if it is at rest, there is no kinetic energy. Okay, last exercise. Give an example of a moving object that has both translational and rotational kinetic energy. Illustrate with a drawing or diagram. So you can actually have different examples for this, but my example is a rolling ball. This is the direction of the rotational kinetic energy, and this is the direction of the translational kinetic energy.